Hello, welcome to Lecture 4 of the online course on Explainable Machine Learning and Artificial Intelligence. This will be the first lecture in a series of 2 on inherently interpretable models. In this first lecture, we will focus on linear regression, one of the most fundamental and general interpretable models. This course assumes that you are already familiar with linear regression. It's one of the prerequisites. So today we will start with a short reminder about linear regression and then use it to introduce some fundamental concepts in the field of interpretable machine learning and artificial intelligence. The specific goals of this lecture will be, first, to review what interpretable models are in general, then to review the basics of linear regression. We will then focus on explaining when linear regression is interpretable, and use linear regression to define feature importance and attribution, 2 central concepts in all of explainable and interpretable machine learning. Within linear regression, we will then discuss the trade-off between predictability and interpretability, another key concept. Finally, we will outline 2 additional methods for interpreting linear regression called the geometric and neural interpretations. But before we start, let me step back and remind you of what we are trying to achieve. The goal of explainable machine learning is to develop models that provide explanations to human users for the decisions that they produce. So a key question is how to generate explanations from a machine learning model. Going back to the machine learning pipeline, we have already seen that one approach for generating explanations is to use models that are inherently interpretable. This is the approach that we will be focusing on in this lecture and the next one. What are inherently interpretable models? They are models that obey a series of criteria. The first and strongest criterion is simulatability. This is the ability to internally, mentally simulate the model and reason about its full decision-making process. In particular, this implies directly understanding how individual inputs and individual parameters affect the outputs of the model. The second, weaker criterion is modularity, which refers to the possibility to break up the model into smaller parts that can be understood separately. The third criterion is that the inputs on which the model acts need to consist of features that are interpretable to the users, meaning that they are either domain-based or specifically engineered to be interpretable. More concretely, there is a series of properties that facilitate interpretability in a model. The first property is linearity with respect to input features. Beyond linearity, a second property is monotonicity of the output with input features, meaning that the output either increases or decreases monotonically when an input feature is increased. A third crucial property is sparsity. A model is said to be sparse when it depends only on a small number of features, and that helps with interpretability because it makes it easier to understand which features determine the output. This is a key property that will come back repeatedly. One property that plays against interpretability are interactions between features. So the fewer interactions there are, the more the model is interpretable. Finally, because the explanations ultimately need to be understandable to the audience they address, interpretable models are in general field-specific. Nevertheless, there are several classes of models that are used in many different fields, and that can be considered to be interpretable. The first and most general class of models is linear regression. A closely related class are models of linear classification, and 2 additional classes are decision trees and rule lists. In which sense are these models interpretable? This table, taken from the book on Interpretable Machine Learning by Christoph Molnar, shows how different examples of models satisfy the properties that I just discussed: linearity, monotonicity, interactions. In the final column, we can see the types of tasks the models can perform, either regression or classification. Linear regression, as its name suggests, is a linear model of input features and therefore also monotone. It includes no interactions between input features and is therefore potentially highly interpretable. Logistic regression is a specific type of linear classifier, but it is actually not linear in input features. It is nevertheless monotone and includes no interactions, so logistic regression is a common reference for an interpretable classification model. Decision trees are neither linear nor necessarily monotone, and they do include interactions, so they are interpretable under specific conditions. And the situation is quite similar for rule lists. In today's lecture, we will focus on linear regression and then cover the three other classes of models in the next lecture. So let's start with a reminder of basics of linear regression. To start with, remember that we have defined a model as a function that takes as an input one instance, which is a vector of values for p features. The model then maps this input onto an output, which is also called the prediction of the model. Linear regression is a subclass of models in which the output is a linear function of input features. That means that the output y is obtained by multiplying each input feature x by a corresponding feature weight beta, and potentially adding a constant intercept, as well possibly an independent noise. So in linear regression, the model parameters are usually called the betas, and they correspond to the coefficients of individual features. Training a linear regression model then corresponds to estimating optimal values of feature weights beta by optimizing a cost function. Various cost functions can be used, but the most basic one is mean squared error, which consists of differences between model predictions and actual outputs squared and then summed over the training set. Optimizing mean squared error by adjusting feature weights in a linear regression model is usually called ordinary least squares. And the standard way to determine optimal weights is to compute what is called the pseudo-inverse of the input data matrix. I will not go into the details of this. The point here is that they are very standard algorithms for training a linear regression model, and these algorithms give us an estimate of both the optimal weights and the standard error on the weights. Once we fit the model, we need to quantify how good it is. And for this too, there are very standard methods for linear regression. A standard way to quantify the quality of the model is to compute the fraction of variance explained, usually called R-square. Importantly, this has to be computed over the test set. To compute this metric, the first step is to compute the squared sum of error, which is the difference between model outputs and true outputs, squared and summed over the testing set. The obtained quantity then represents the remaining variance, that is, the amount of variance in the output that is not explained by the model. The remaining variance is then compared to the total variance in the output, in which individual outputs are compared to their mean over the dataset. Finally, R-square, the explained variance, is computed as 1 minus the remaining variance divided by the total variance. If the prediction is perfect, R-square is 1. If the prediction is equivalent to just outputting the mean, R-squared is 0, and if the prediction is worse than the mean, R-square is negative. So fitting a linear regression model is a very well-studied problem for which we have standard validation methods. Let's now turn to how we can interpret the model that has been fit. Let's imagine we have fit a linear regression model to a dataset. We next use this model to make predictions for new data, but together with predictions, we want to provide the users with explanations on how the predictions were obtained. A key question is, how much does each input feature contribute to the output, assuming all other inputs are fixed? Quantifying the contribution of each feature is called computing the feature importance. Within linear regression, a natural quantification of the importance of each input is the corresponding regression coefficient beta, in the sense that strongest weights contribute most. So a naive quantification of feature importance is directly provided by the regression coefficients. Why do I call it naive? Because in reality, different features can have different scales and different variances, so that some input features can take much larger values than others. To take this into account, the general recommendation is to use centered and rescaled features, and in this case, regression coefficients provide us with feature importance scores that can be compared across features. If the data is not centered and rescaled, an alternative is to directly rescale the estimated coefficients by their standard error. This is usually called the t-statistic, and this gives us an alternate way of computing feature importance. Comparing regression coefficients, or t-statistics, across different features provide us with an explanation on how different features contribute to the output over the whole dataset. This gives us a so-called global explanation of the model, which describes which features matter most in general. But we might want to explain the output for one specific instance rather than the whole dataset. This is called a local explanation, and this is what we want typically to provide to the end user, the user for which the decision was made. If we want a local explanation for a specific instance, the coefficients in a linear regression model are not the right quantification. Even if the regression coefficient is large, in a specific instance, the value of the corresponding feature could be small or even zero. So if we look at a specific instance j of the output, for each feature I, instead of the regression coefficient beta I, we can compute the product of the input feature value xij and the regression coefficient beta I. This is usually called the feature contribution or effect size, and it directly tells us how much feature I contributes to the output in instance j. This was the general theory for linear regression. Let's now apply these concepts to a textbook example. Let's look at the classical bicycle rental dataset, a standard example available online. This dataset contains the daily count of bicycles rented by a company, and in this dataset, each instance is a day of the year. The input features are the season, temperature, humidity, wind, and whether the day is a holiday or a working day. The output is the number of rented bikes on that day. So the goal is to train a model to predict the number of rented bicycles, and for this we can simply use a linear regression model. This table summarizes the parameters of a fitted linear regression model. In the first column on the left, we have the input features. In the second column, we have the fitted regression weights. And in the third column, the corresponding standard error. Note that here the inputs were not centered and rescaled, so the weights take very different values over different features. One way of comparing them is to compute the t-statistics, which is the ratio between weights and their standard error. These t-statistics give us directly a quantification of the importance of different features. In this particular example, they showed that the most important feature is the number of days since 2011, because the business in the company, the number of rented bikes, has been increasing since the start of the company. The second most important feature is the temperature, how cold or hot it is on the day that we are considering. And these statistics show that this is overall an important parameter that explains the number of predicted bikes. So the feature contributions provide us with a global explanation of the importance of different features in the whole dataset. To look at local explanations for individual instances, we can look at effect strengths. The effect of feature I in instant j is given by the product between the regression coefficient beta I and xij, the value of feature I in instance j. This gives us one number for every feature in each data point. Over the whole dataset, the distribution of effects can be visualized with a box plot, and this is shown in the figure on the right. For each feature here on the y-axis, the box in a box plot contains the effect range for half of the data, and the vertical line in the box is the median effect. So the size of the boxes show the feature contributions on the global level in a manner similar to t-statistics. We see again that days since 2011 and temperature have globally the largest contributions. To explain one given instance, we can plot the effects for this instance directly on this graph with 1 point for each feature, shown here as red crosses. For this example feature, the predicted value, 1,606, was much lower than the mean, which was 4,504. Plotting the effects of different features explains that this low value of the prediction was in particular due to the fact that the temperature was much lower than average that day, and the day on which this prediction was made was early in company's history, close to 2001. Note that here the data was not mean-centered, so the natural comparison point for each feature is the center of the corresponding box, and not 0. If the data was mean-centered, the natural comparison point for the effect of each feature would instead be 0. So linear regression models can be used to directly provide explanations for the outputs by using regression coefficients as a quantification of feature importance, and by computing individual feature effects for individual instances. But are these explanations good explanations for human users? What does it mean to have a good explanation for human users? In Lecture 2, we went through a list of criteria. Human-friendly explanations need to be social in the sense that they need to be adapted to the knowledge of the audience. They need to be short to minimize cognitive load, contrastive to explain why one decision rather than another one, and generally selective rather than exhaustive. So, does linear regression provide good explanations based on these criteria? First, are the explanations social? This point depends on whether the features used by the model are directly interpretable and meaningful for the audience. Are explanations short? Well, this depends on the number of features in the model. If the model includes many features, and many of them have large coefficients, then it becomes difficult to mentally keep track of the contributions of these features. One way to make linear regression more interpretable is to minimize the number of features with non-zero coefficients, or inversely to have many features with zero coefficients, and this is called sparse linear regression. Are explanations contrastive? A natural point of comparison in linear regression is an instance where all features are zero. This point of comparison is meaningful if the data was mean-centered, because in that case the instance with all features zero is precisely the mean of the dataset. Therefore, explanations obtained from linear regression become automatically contrastive if data was mean-centered. So altogether, linear regression is interpretable if the individual features are interpretable, if they are mean-centered, and if the regression is sparse, in the sense that only a small number of features have non-zero weights. This last point, sparsity, is something that can be directly optimized for. And by optimizing sparsity, we get what is called sparse linear regression. How can sparsity be automatically optimized in a linear regression model? This can be seen as a constrained optimization problem. Starting from standard linear regression with mean square error loss function, the goal is to minimize the loss function, which quantifies the error on the prediction, and at the same time minimize the number of non-zero coefficients. One of the seminal results in the field of statistical learning is that this can be achieved by using the so-called lasso constraint, which consists in minimizing the sum of absolute values of regression coefficients. Using a Lagrangian formulation, this optimization problem can be expressed as the optimization of a composite loss function that consists of the sum of the prediction error, given by mean squared error, and a lasso regularizer, which enhances sparsity and is multiplied by a regularization parameter lambda. The key point is that this lasso regularizer on the right-hand side can be interpreted as a measure of model complexity. The more non-zero coefficients the model has, the more complex it is, and the larger this lasso regularization is. So, optimizing this composite loss function effectively leads to a trade-off between optimizing prediction quality, this is the first term in the loss function, and optimizing interpretability or model complexity, this is the second term. And this trade-off between predictability and interpretability is controlled by the parameter lambda. The trade-off between prediction and interpretability is one of the key concepts in interpretable machine learning. In general, increasing interpretability comes at the cost on the accuracy of predictions. Yes, how much prediction accuracy is really lost by focusing on interpretable models is a topic of a heated debate, and we will come back to this later in the course. In the last part of this lecture, I will discuss two additional ways to interpret outputs of linear regression, the geometric and neural interpretations. These two interpretations will be useful later in the course. The geometric interpretation consists in rewriting the output of a linear regression as a scalar product between two vectors. A vector beta containing the regression coefficients and a vector x containing the feature values for a specific instance. These vectors are of dimension p plus 1 because we include one constant term for the intercept. The scalar product can then be interpreted geometrically in the so-called feature space, the space where each axis represents the values of one feature of the inputs. The simplest example is the case where there are two features and no intercept. The feature space is then two-dimensional, and the vector beta defines a direction in this space, shown in red here, as well as a direction orthogonal to it, shown in gray. This direction orthogonal to beta defines sets of inputs that have different feature values, but lead to an identical output because they all have the same scalar product with beta. So the level lines of the output are straight lines orthogonal to beta. Going beyond two dimensions, in general, the beta vector defines a direction in feature space, but the sets of points orthogonal to beta now define hyperplanes containing inputs that all lead to the same output value in the linear regression. So in general, the level lines for linear regression can be interpreted as hyperplanes orthogonal to beta, shown in gray in the figure on the right. Another interpretation of linear regression is to represent the output as the output of a linear neuron, illustrated here. This neuron receives individual features as inputs and multiplies them with synaptic weights corresponding to the regression coefficients. This interpretation will be particularly useful in the future lectures when we start dealing with neural network models. This brings me to the end of this lecture, where I have reviewed what interpretable models are and reviewed the basics of linear regression. Most importantly, I have explained what it means for linear regression to be interpretable and used it to introduce the central concepts of feature importance, feature contribution, and predictability-interpretability trade-off. Finally, I have outlined the geometric and neural interpretations of linear regression. In the next lecture, we will continue exploring interpretable models, but we will go beyond linear regression and talk about linear classification, decision trees, and rule lists. Stay tuned and see you next time.